Hello, class. We'll wait one more minute and then get started. Hello? Hi, Bugger. Come here, man. Come here, Bugger dude. Well, it's a real cool Bugger dude. What's up, Bugger dude? What's up, Bugger dude? How's it going, big man? Bugger, 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 bugger. Well, thanks for that num-num, man. I appreciate it. Well, you're the cutest little boy. You're the cutest little boy. Okay, get out of here. Go. All right, I'm going to get started. All right. So today's going to be our last lesson on electric potential. So today's lesson is about electrical potential energy. So now we have that energy on there. So now we're talking about joules, okay? So let's imagine that you have a charge Q1, all right? And then, so that charge creates a electric potential, okay, around it. And then we put a charge Q2 in that electric potential, and it is a distance r away from the charge. Then from the definition of electric potential, the electrical potential energy is Q times V. So the charge is the charge that we placed in the electric potential. So that's Q2. And then the potential is the potential created by Q1, which if you have a single charge, it's K Q1 over R. All right. So what that means is that if you have just two charges, the electrical potential energy of them is K Q1 Q2 over R. So the electrical potential energy in joules is given by that formula. It's pretty rare that you just have two charges. Normally you have a system of many charges. So if you have a system of many charges, then the total electrical potential energy is going to be K Qi Qj over Rij sum over pairs. So what is Rij? Well, Rij is the distance between charge I and charge J. All right, so we sum over all pairs. So it's just this equation summed up over all the individual pairs. You want to make sure not to double count. So the pair ij is the same as the pair ji, so you don't double count. You might recall that this is the exact same formula as for gravity. I believe we talked about this with gravity, the total gravitational potential energy of the system. So let's do an example. So the example is going to be fairly simple. We got a right triangle of charges. This is a -2 times 10 to the -4 Coulomb charge. This is a -7 times 10 to the -4 Coulomb charge. And this is a +5 times 10 to the -4 Coulomb charge. And we're going to make this a 3, 4, 5 right triangle. So 3 meters, 4 meters, 5 meters. I know I kind of goofed and I wrote this as 3. Oops, my bad. This distance is shorter than that, but I wrote it as 3. Oopsies. So I'm going to apply this formula. I want to know what is the total potential energy of this system. Okay. So we have U equals K K just, I could, if I wanted to, I could just factor K out of this entire sum. All right, so that's what I'm doing here. And there are 3 pairs. There's this pair, there's that pair, and then there's the hypotenuse pair. So let's do the horizontal leg pair. So that's going to be Q1, Q2 over R, which is 3, plus, now let's do the vertical pair, Q1, Q2 over R, which is 4. And then now let's do the hypotenuse pair. There we go. All right. So going to the next line, I'm just going to simplify this a little bit. 10 to the -4 times 10 to the -4 is 10 to the -8. Okay. So notice how we have 10 to the -8 here. All 3 of the terms have 10 to the -8. Okay. 10 to the -8. So I'm going to factor out that 10 to the -8 and bring it out front so that it multiplies the 10 to the 9th. 10 to the 9th times 10 to the -8 is 10 to the 1 power, which is also known as 10. So when I factor out all these 10 to the -4s, it's going to make this go to 90. 9 times 10 to the 1. All right. Then I have 5 times -7, which is -35. -2 times -7 is 14. 5 times -2 is -10. So I have to work this out. and I get a total electrical potential energy of 915 joules, which is, so this is the total electrical potential energy, which is less than 0. So whenever you have a potential energy that is less than 0, this tends to indicate that the system could be bound. Bound meaning that these particles are stuck together, okay? Because we have negative potential energy. So that's the first type of problem that I would like you to know how to solve, is how do we calculate total electrical potential energy of a system of charges? Pretty straightforward. Another type of question I would like you to know how to solve is to figure out how much energy would it take to remove a charge. Okay, so what if I wanted to take this charge and just pull it away? So remove it, I mean move it away to infinity. So I take it and I go whoosh, and I move it really, really, really far away. Okay, well, you start out with an initial amount of potential energy, and you end up with a different amount of potential energy. So U final is the potential energy with the charge removed. Okay, obviously you could also do this with adding a charge. Okay, and so conservation of energy says that the initial energy plus the work done is equal to the final energy. So what we can do is we can use this conservation of energy law to calculate the amount of work, which is the energy it would take to remove a charge. Does that make sense? I hope it does. So let's do another example where we have let's take that previous problem, all right, the right triangle, and what we're going to do is we're going to remove this charge. So we're going to keep these two charges, and we're going to take the one that was right here, and we are going to take it away to infinity. It's going to go away and never come back. All right? And we want to know how much work would this take? Okay? So I'm going to use the equation from last time. So we have U initial plus work equals U final. Now, this is the same system as I'm not going to redo the calculation. It's the same system that we just did, okay? So I know that the initial energy was negative 915 joules, okay? I'm trying to find the amount of work done. So now what I have to do is I have to find the final total electrical potential energy of this system. Okay, so as you can see, this charge is gone, so we only have one pair. All right, so it's two charges that are 3 meters apart. One is 5 times 10 to the minus 4. The other one is negative 7 times 10 to the minus 4. So this is just two charges, so there's one pair. The final electrical potential energy is therefore K Q1 Q2 over R. All right, So let me plug this into my calculator. And I get negative 1,050 joules. Okay, so I have negative 915 plus work equals negative 1050. So then I add 915 to the other side, and I get that the work required to remove this charge is negative 135 joules. So what does that mean? What that means is that, so remember, work, if you do work, you are adding energy to a system, okay? So if I said you do negative 135 joules of work, that means that you actually receive 135 joules from the system, okay? So what that means is that you could extract 135 joules from the system by letting the charge leave. What that means is that this charge wants to leave, okay? So actually, to make this system, you would have to like hold it in place. You would have to bolt these charges down. And then once you just remove the bolt, that other one is just going to go off to infinity, okay? It's pretty easy to understand why that would be the case. If we look at the original system, so opposites attract and likes repel. So this charge is going to be repelled by that one, okay? And then the charge is going to be attracted by that one. But the repulsion is greater than the attraction for the following reason, okay? The repelling charge is closer, 4 meters away versus 5 meters away. And the repelling charge is bigger in magnitude, so negative 7 versus 5. So this charge is closer, and it is a bigger in magnitude, and so the result is that this charge is going to get pushed away. All right. There you go. So there is a third type of problem that I would like you to know how to do, which is calculating closest approach. Okay. So here's the setup for the problem. So we have a nucleus. So as you know, a nucleus is a bare positive charge. So I'm not talking about the electron cloud around the nucleus, just the nucleus itself. The nucleus has a charge of plus Ze, where Z is the atomic number, and E is the fundamental charge, which, if you recall, is plus 1.6 times 10 to the minus 19 coulombs. Okay? So that is the fundamental charge. So, for example, and then Z is the atomic number. So, for example, if we were talking about carbon, carbon is atomic number 6, and so therefore its charge would be 6. The charge of its nucleus would be 6 times 1.6 times 10 to the minus 19. So 9.6 times 10 to the minus 19 coulombs, because there are 6 protons. There are also 6 neutrons, but they don't count towards the charge. We assume, okay, the nucleus is massive enough that it doesn't recoil. Okay, so basically what that means is that the kinetic energy of the nucleus is zero, or is really close to being zero, because the nucleus is so heavy that it just stays in place. All right. So then what we're going to do is we're going to launch something much lighter at the nucleus. Okay, so we have a little particle that has a charge of plus E. So it has less charge. It's just a single fundamental charge. And then it has a mass, which we will call M, where M is much less than the mass of the nucleus. Okay? And so what that's going to do is it's going to ensure that the nucleus doesn't recoil very much. Okay? We're assuming that the mass difference is so great that the nucleus hardly recoils at all. And so this charge starts out really far away, and we launch it towards the nucleus, directly at the nucleus, with a speed v. Okay? Now, these two both have positive charges, so they're going to repel each other, but they start out heading close to each other. So what will happen is that this approaching charge is going to get closer, 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 and as it gets closer, it's being repelled, so it's going to slow down, and eventually it's going to come to a distance of closest approach, and it's going to stop. And then what will happen is that once it's stopped, it'll get pushed back in the opposite direction. Okay? So what we want to do is we want to find this distance of closest approach. And we are going to use conservation of energy to do that. Initial energy equals final energy. So initially, we have the kinetic energy of the approaching particle, which is 1/2 mv squared. All right. And then we also have the electrical potential energy of these two charges. So you've got K, Q1, Q2, so E times ZE, over, now they start out really far apart, okay? So they start out an infinite distance apart. Because they start out really far apart, divided by infinity, this term drops out. And remember, the nucleus is at rest, so it doesn't have kinetic energy. At the closest approach, the approaching particle is now momentarily at rest, so we have no kinetic energy at the closest approach. Okay? If we did have kinetic energy, it would still be moving closer. So all we have at closest approach is electrical potential energy. All right. So going down to the next line, we have 1/2 mv squared equals k z e squared over d. And then solving for d, I get d equals 2 kz e squared over mv squared. All right, so that's how close it's going to get. Now, this equation makes a ton of sense to me, okay? As the mass and the speed of the approaching particle increases, this particle is going to have more, it's going to have more momentum, which is going to allow it to get in closer. D is going to be smaller. So as the momentum of the approaching particle increases, it is able to get closer, smaller d. If the nucleus has more charge, it's not going to be able to get as close, okay? Because there's going to be more electrical repulsion. So we can see that as z increases, the distance of closest approach gets larger, it gets further away. All right? So this equation makes great intuitive sense. Now, here's something interesting. We could say, well, what if the distance of a closest approach is approximately 10 to the minus 15 meters? Well, correct. It can never actually touch it. Not without infinite momentum. So yeah, what if the distance is 10 to the minus 15 meters or less? And so in this case, so it turns out that the nucleus is made up out of positive charges, right? So if we just looked at the nucleus, it wants to break apart electrically, okay? But there is another force in the nucleus. It's called the strong force, okay? And the strong force is strong enough to hold the nucleus together, even though it has all positive charges. So the strong force is stronger than the electrical force. That's why it's called the strong force. It's so strong that even though the protons in the nucleus are repelling each other electrically, the strong force is stronger than that repulsion, and the nucleus holds together, okay? But the thing is that the strong force only works if the two particles are really, 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 really close together, okay? And you have to be about 10 to the minus 15 meters apart in order for the strong force to kick in, okay? And so if you have a large enough speed such that you could get within 10 to the minus 15 meters, then the strong force might take over and you could have fusion occurring. So that means that the particle has gotten so close that the strong force takes over and this particle becomes part of the nucleus. You have fusion, okay? One of the interesting things, okay, is usually we don't control the speed of the approaching particle directly. What we control is temperature, okay? And it turns out that temperature T, all right, is temperature T is equal to a constant, which I'll call C, times the average kinetic energy per particle. Okay? And, okay? So right here on the left-hand side of this equation, we basically have temperature, because temperature is average kinetic energy, and that's kinetic energy. So we could say, if we wanted to, we could say temperature equals, and then I'm temperature over C, but I'm then multiplying that C over, C, K, Z, E squared over D. All right? So if the temperature is this, then that is how close the particles are getting. All right? Now, if we set that distance equal to 10 to the minus 15 meters, this tells us what the temperature at which fusion would occur. All right? So basically, this is giving us an idea of the interior temperature of the sun. Okay, because we know that the sun is powered by fusion, and so it needs to. The center of the sun needs to at least be this temperature in order for fusion to be occurring. Okay, but there is one more subtlety here, which is the following. I believe when I talked about potential energy graphs, we talked about tunneling. So, so this temperature is too big. We actually observe fusion occurring at a lower temperature, a temperature that is lower than this one by quite a lot. I can't remember what the factor is, but it's like this temperature is really too big. We see fusion at much lower temperatures. And the question is why? Well, when we take into account quantum mechanics, okay, quantum mechanics has this idea called tunneling, which is when a particle is able to go into a region where it's not supposed to go. It doesn't have enough energy to go there, but it ends up there nonetheless. And that is possible in quantum mechanics. Okay? It's not possible in classical physics, but it is possible in quantum mechanics. And guess what? The world runs at its deep level on quantum mechanics. So what happens is you don't have to get within 10 to the minus 15 meters. You get around that, you can get further away. If your closest approach is further than that, the particle can tunnel the rest of the way and fuse. Okay? And so so basically we have tunneling occurring, which allows fusion to occur at a much lower temperature than it would occur at if we had only classical physics. So that's a good thing. It allows stars to work the way that they work. If that wasn't the case, then stars would have much different physics. All right, so we've learned 3 things today. We've learned how to calculate total electrical potential energy. We have learned how to calculate the work required to add or remove a charge. And we've learned how to calculate the distance of closest approach. There's a 4th thing that we learned in the last lesson, which was how to find the period of small oscillation if you have a charge that's in a system and it's oscillating. So those are the 4 questions that are on today's quiz, and I will see you in the Zoom room.